One of my favorite things about math is that seemingly unrelated topics have surprisingly deep connections. This video will talk about one of my favorites, the Ising Model, which while introduced as a model for magnetism, has been used as a model for meltponds in Professor Ken Golden's recent research. The Ising Model was originally developed to study a key phenomenon in physics called ferromagnetism, which is how certain materials become magnetized. In a ferromagnetic material like iron, the atoms have tiny magnetic moments, like little arrows that can point up or down. Generally, all of the atoms are random, but if you put a magnet close to iron, then all these moments become aligned and the material becomes magnetic. In physics, systems usually want to have the lowest energy possible, and a ferromagnetic material is no exception. If an atom aligns in the same direction as the external magnetic field, then that lowers energy. In addition, atoms which share the same direction as its neighbors have lower energy. Now the question is, how do we represent these characteristics of a ferromagnetic material analytically? At the heart of the Ising model is something known as the Hamiltonian. Like I mentioned before, systems usually want to have the lowest energy possible, and this function is the system energy. So keep in mind that we want to make H as low as possible. Note that for simplicity, I'll represent a ferromagnetic material using a 2D lattice, where red corresponds to an atom pointing up, and blue corresponds to an atom pointing down, and the value in each square refers to the magnetic field at each point. Each eye refers to one square of this lattice. SI refers to the spin of each atom, either +1 for up or -1 for down. HI refers to the external magnetic field. There are some versions where the magnetic field is constant for each site, but the version I'll be using is known as the Ising free energy model, where the magnetic field is unique to each site. Each J refers to neighboring atoms for I, with their own corresponding spins. In the case of a 2D lattice, there are 4 J's for each I. Lastly, Jij refers to how strongly the neighboring atoms influence each other, which is known as the coupling constant. Note that if Jij is positive, then neighboring atoms want to have the same spin, which is the assumption we'll use. Let's now go into each sum and explain what it means. If Hi and Si have the same sign, that is, the atom has the same spin as the external magnetic field, then this sum becomes negative and thus reduces the energy of the Hamiltonian. Likewise, if they have different signs, then the negative on the inside cancels with the negative on the outside, which leaves a positive sum, which adds to the total energy. The second sum is used to consider how neighbors influence each other. If the spin of I and spin of J have the same sign, then the interior of the sum will be positive, and this also reduces the energy of the Hamiltonian. And likewise, if the spin of I and J have different signs, then the interior of the sum will be negative, which cancels with the negative on the outside, and this adds to the total energy of the Hamiltonian. In the case of our lattice, a state with lower energy corresponds to one where there are clusters of the same spin, and generally the color corresponds closely with the external magnetic field, with positive values being red and negative values being blue. But now let's shift our focus away from magnets and into something a bit different. In late spring, the snow on top of sea ice starts to melt, which leaves small ponds of water. As time goes on, these simple melt ponds combine with others and form these long, maze-like structures. And furthermore, ice is white, which means that solar radiation is reflected away. However, water is dark blue, which means that it absorbs more solar radiation and allows light to pierce through into the lush ecosystem below. Thus, these melt ponds help determine the rate that ice melts, the amount of energy entering these systems, and so on. Thus, it's pretty important to figure out how to model this phenomenon accurately, which, if you've been paying attention, you may have the guess we can do with the Ising model. But to help spark the connection between meltponds and magnetism, and why the idea of using a magnetic model works in this scenario, take a look at these images. On the left is a showcase of magnetic domains in cobalt, which are approximately 20 microns across. On the right is an Arctic melt pond, approximately 100 meters across, and at first glance, these appear to be really similar. Here's another pair of examples. On the left is a microscope image of maze-like domain structures in thin films of cobalt iron boron, which is used in magnetic memory using something known as the magneto-optical Kerr effect. This effect is interesting enough to make its own video on, but for now, just note that this is another image of magnetic domains. On the right is a similarly structured meltpond, roughly 70 meters across. Thus, there does appear to be a connection. What Golden does to model these meltponds is take the Ising model and give different definitions for the constants. The main difference is that instead of magnetic spin, +1 means that the square is meltwater, and -1 means that the square is ice. Then Jij, instead of representing the coupling constant for magnetic charges, simply represents the fact that water tries to combine with water, and ice tries to combine with ice. Lastly, the external magnetic field can be represented as the topography of the snow. Specifically, we have h minus hi, where h is an initial reference height. Gravity dictates that meltponds form in the lower areas and ice forms at the peaks since it hasn't melted yet. Thus, if the height is more than the reference height, then h minus hi is negative, and if the type of the square is ice, which has -1, then the negatives cancel out and the energy is reduced. Likewise, if the height is less than the reference height, then h minus hi is positive. Since meltponds have SI equals 1, then you also have a negative sum which reduces energy. And similarly, with the magnetic Ising model, if two adjacent regions are both ice or both meltponds, then the total energy is reduced. If we apply the Ising model to a random ice topography, we can see that what we end up with is similar to what happens in reality. But to really show this effect, here is a bigger grid. The meltwater clusters and the ice clusters in the final arrangement align really closely with what is observed in real life. The final configuration is a metastable state, a local minimum of the Hamiltonian. As neighboring sites exchange heat, the spins tend to align to minimize energy, and it means they transition from the purely random initial state to something with a little more order. This phase transition is essential to a lot of problems in statistical physics, and is an indicator we're doing something right with this model. Hope you enjoyed the video.